Thank you very much. So let me start by thanking the organizers for the invitation and for the opportunity to speak here. Very nice conference you put together. This for if you ask too many questions. Very good. So, so this is a talk about some joint work that had been going on for a few years now with proper subsets of these people. So Pietro, Sibasic, Rafael, and Johannes. I'm going, of course, not talk about everything, but I'm going to talk about one aspect of them. And then Sibasic is going to talk about some other aspect in the next talk. So all the difficult questions, please redirect them to him. So let me start with a motivation, so you know what's the problem we are solving, and then I will tell you what the approach I will take. So first, the motivation. So the motivation, of course, it's a very noble motivation, very noble goal. So this is kind of the most general. So many talks here had been about Donaldson-Thomas invariants. So if we take X some Calabi-Yau threefold, given an object, we can define, let's say, we are implicitly thinking of near a large volume point in the Kähler moduli of X. So we can define the B-branes of X, usually called sometimes topological B-branes, by the derived category of coherent sheaves on X. However, if you want to define Donaldson-Thomas invariant, let's say we take an object here B, it's not enough to consider topological B-branes, but you have to consider stable B-branes. So you have to have the space of even price plus some stability conditions. So stability conditions are usually the way we define it. So there were some in the talk by Sergey. They are defined for a given brane, and also in terms of what I'm going to denote like this, just the charges of the B-brane. So it's a point on the lattice of charges. So giving these B-branes and some stability conditions, if we call its lattice of its charge of this object Q, we can compute a number that's called the Donaldson-Thomas invariant associated to this B-brane and a set of stability conditions. What I'm here implicitly, as I said, I'm in what you will call the large volume chamber. Or we can write it sometimes just like this to say it depends on the Q. So for physicists, what we are doing roughly is counting bound states of B-branes of this given charge. Counting stable bound state of B-branes of this given charge. So the objective is now to answer the question. So you can answer the question given the A side of this. So given, let's say, for example, the Fukaya category of X can define some stability conditions. Can we define something like dt, some number, I will call it omega, because omega appears a lot, omega associated to an object here, which is typically a Lagrangian submanifold with some U1 local system. In this case, I'm always going to consider U1 local system. So this is some A-brane. So is there a number here that actually we are going to see? It's going to be a number that depends on the class of L. It's going to depend on the class of L here. And some stability conditions, right? So in the case of the Lagrangians, we have a way to stable is equivalent to say that L is a special Lagrangian submanifold of X. it doesn't go all the way to here. That's sorry. So the question we are trying to ask is how to compute this omega of L. How to compute this? So this should be equivalent to dt of some mirror of L, or mirror of L delta, where mirror of L delta belong to the derived category of coherent shifts of the mirror of X. So the question is how you compute this, how you compute this in this side. Of course you can think of many ways. There are many proposals how to do this, but we are going to do something very concrete here. Now, so the idea is how to compute. Without, of course, without referring to the mirror. That's otherwise there's no point, right? So you want to compute just purely studying the Fukaya category and special Lagrangians on a particular geometry. So of course, solving the problem in general is really hard. This is going to be a complicated problem. So, so the idea, this is what we did with Pietro et al., is to concentrate on a very simple setting. So what is this very simple setting? We are going to focus on the case that X is a conic bundle. Actually, a very special class of conic bundle. So I'm going to give you X is going to be something very concrete. So it's going to be like this. Where f of xy is some Laurent polynomial here. So this is the case we are going to concentrate. Why? Because well, these cases are very amenable because you are going to see two techniques that we borrow from spectral networks, and we call them exponential networks. And also another thing is that, of course, the mirror of X is a toric Claviau threefold. Therefore, all these invariants have been computed by several tons of techniques. So if we compute any number here, we definitely know what to compare. We just need to know this mirror map. Okay, but in this case, this type of questions have been analyzed so very deeply by other people. So we can just borrow their results. That's right, because it's a toric Claviau threefold, right? So this is non-compact, mirror is also non-compact. Everything is non-compact. So, okay. So what we are going to do is to study then Lagrangians on this, So how? So now the question is, what's the approach? So how we do it? How we do the computation of this omega? And this is going to be studying, we are going to use one fact. So we're going to use one fact is that slugs, or certain classes, I should say certain classes of slugs in X are in correspondence with slugs in sigma, where sigma is going to be this so-called mirror curve. This is very vague. This is very vague. We are going to make it more concrete as we go. So just to fix notation, sigma is going to be embedded in C star cross C star. So once C star, I put an X here to the X coordinate and Y here for the Y coordinate. Okay, because I'm going to use this notation. So we are going to study slags on this so-called mirror curve. That's what we are going to do. And we are going to define some counting. And then it's like, so this is a fact. And then we are going to define some counting, which is going to give us omega of gamma, of some gamma, some Lagrangian. Okay, so how we are going to do this, how we are going to define this counting, and this is where all the machinery enters, okay? So it's going to be in two steps. So the first step, I'm going to define, for you, this gadget that's called exponential networks. And the second step, I have to say, if you look at the series of papers we have two ways of defining this number. And I'm going to concentrate on one of them, and I think Sivasic is going to talk more about the other one. So the way I'm going to do it is define another gadget that is called the non-Abelianization. So it's good to better call it NA map for exponential network, which I'm going to denote it like this, but I'm going to define it for you. Non-Abelianization map, something that depends on the network. And actually, what we really are interested in, something called jumps of such non-Abelianization map. So I have to introduce for you these two things, and probably most of the talk is going to be the introduction of these two things because they are a bit technical. Yeah, please. Correct. Okay, that one is like a limit of this in certain cases. So this is, I'm going to describe a very analogous setup than that, the spectral networks. Those are the spectral. I will go, okay, let's go step by step. So first we do, the exponential networks. So exponential networks. So there are a lot of things here. So for the exponential networks, the first thing we have to do is to think of sigma, equip sigma with one form. So for the people who are familiar with spectral networks, this follows very closely many of the machinery there. Some of the things we do is like heuristically follow them in this, but translated into this setup. So some of them are not, some things are not super well motivated. Some things are well motivated, but at the end of the day, we get correct numbers. So that's a positive thing. So this the one form here is going to be of this form. It's going to be this one, which is right. It's the Liouville one form of the standard holomorphic volume form here. So this one, of course, restricted to sigma. So I'm going to keep this as my holomorphic one form, really logarithmic. It has logarithmic singularities, as you can see. It's multi-valued in sigma. And that's exactly why this is called exponential networks and why everything is more complicated. And I'm going to fix sigma. I'm going to fix some maps on sigma. So I'm going to think of sigma as a branch cover over a base. So the base I'm going to choose is just C star of X. This I'm going to call C, to an analogous with the base curve of the spectral network, but here really C is just this. And usually, kind of the setup Vivek was talking, it stopped here, and then you start looking for some cycles calibrated by lambda, etc. But in our case, the problem is, as you can see, lambda is multi-valued still on sigma. So I have a problem here. So I cannot just work on sigma very comfortable. So how you solve this problem? So the way we solve it, which maybe it's not, some people can say it's not the smartest way to solve it, but it's the way we solve it. If you have a better way, you are welcome to tell me or to do it yourself. And yeah, that's it. So what we are going to do is, instead of working on sigma, we are going to have to work in kind of an auxiliary, but rather nasty cover, which is the logarithmic cover. So locally, if I write the coordinates, here the coordinates are going to be x. In sigma, the coordinates are going to be like x, comma, yj of x, where this j are the sheets of this map. Which sheets of this map? Like, for example, it's a finite number of sheets, let's say, depends on the degree of this fxy. But now, as I said, I'm going to work on this one, where the coordinates are like x, comma, capital Y sub j x plus 2 pi I big N, where this N, so this is locally how they look, so this N is just an integer. I hope I'm not writing like super small now, because you can also project on Y. It doesn't. In principle, we argue that it doesn't matter. You can use any other base to project, actually, and you should get the same numbers. We don't have a proof for that, or we don't have a proof for many things, but in particular, yeah, you can project also on X, and you should be able to compute exactly the same way. You should get the same numbers. Right. So where was I? Mm-hmm. Sorry, say again? Yeah. But at this point, it's completely abstract, right? I mean, if I projected on y, I will just exchange y by x on everywhere here. I will. Yeah. Yeah. Okay. Okay. That's that. I mean, if I project on y, I probably would like to change also this lambda a little bit. Yeah, it chooses the way. I'm not sure if I completely catch your question. I choose the lambda the way I like it, because yes, it's probably connected to the question of Vivek, that because I'm projecting on C star of x. So if I were projecting on C star of y, I will choose log of x dy over y. Yeah. Yeah. That's so that's why I meant there is a kind of a choice of lambda in a sense. Yeah, of the one form. Yeah. So, but yes. Actually, there is more. There is more, because you also know there is this framing. There is a whole SL2C transformations you can do, and we also argue that this should be invariant on the DAT. Yeah. That's correct. That's correct. And this computation of these numbers, even though the computation may go differently, at the end the numbers you get should be exactly the same. So particularly if you change the framing, the curve f of xy can be of very different. You can have very different monomials on x and y. And for instance, just a change of framing can change this number here. But still, we argue that the counting should give you the same. So you just choose the most convenient. Don't we always do that in life? Yeah, so what was this? Yes, so there is that. And usually you want to compose this map and so directly work on this thing. So this n here is the logarithmic cover, so it's infinitely sheeted. So now, okay, at least I have to define the exponential networks. So the exponential network that value theta is going to be a collection, of lambda calibrated. I don't know if this is the correct terminology. Calibrated trajectories. I will call it trajectory. I will define it concretely. Okay. So it's in sigma tilde. So what I'm going to define, so what are these trajectories? So the trajectories are solutions to this differential equation. So this comes, there is also some physical motivations for this setup, but I'm not going to talk about this in detail, but I will give you the answer what this is. So this I'm going to call little n, this difference. So this dx d tau 1 over x equal e theta. So the theta is just some fix. So you fix theta in 0 to pi, for example. That's, and you solve, you have this, I'm sorry, this differential equation that depends on theta. This tau is just some real parameter. It's just an ODE. This y depends on x, of course, implicitly, because of they are related by f. This is an equation on f. So this equation, maybe if it looks complicated to you, this is no other thing but like lambda j comma nj minus lambda I comma ni, right? Something like this. It's like, yes, the same equation you will have for the spectral network if you're familiar with that. If not, this is an equation that tells you that the cycle inside sigma tilde is special, meaning it has constant, the differential, this lambda, along this cycle has a constant phase, right? This is constant phase theta. This is literally what this means, okay? You can take any, for this is for any pair aj and for any pair ni and j. Yeah, no, this is not fixed. Nothing is fixed. Here you have to solve a lot of equations and suffer and or have good collaborators. That's it. That will suffer for you. Okay, but that's not enough. That's not enough. That's kind of very empty statement because I need to put some boundary conditions for this. So there is some boundary conditions. So boundary conditions are the following. So I have the boundary conditions. If I put it in words, I still have all the notation there. So trajectories. So these are trajectories at tau equal minus infinity. So it's where they start. If I choose tau to be minus infinity, kind of the beginning of my trajectory, you can choose some other parameterization if you like, are either a branch point, and I'm going to do some pictures so this should be more clear, branch point of pi prime. So a branch point of this up here, or with, so this is a technicality, but this is important, with n equals 0, this little n, this n, or intersection of two trajectories. So okay. So now customary, so it's customary to project these trajectories in same as the spectral network in C. So you project all these trajectories in C, and I'm going to draw you kind of what kind of things can happen, okay? So how this look like in C? So let's say this is C, which remember this is just C is C star with coordinate X, X. Okay. So what can happen here? So what you have here on C, you usually mark several things. Usually you have some points that are removed at x equals 0 and x equals infinity. You may have some other extra punctures, but usually you can fix it so that you only have these two punctures, and you can have a bunch of crosses. So these crosses are going to be the branch points, okay? The branch points of pi prime, the branch point of prime prime. And I'm going to assume always that the branch points, I'm always assuming that all the branch points are simple. So only two sheets of pi prime come together at the branch points, never more. Otherwise, you have to change a few things. And you will have some branch cuts. So if you go, for example, near, suppose this branch point is what we say of type ij, so it means the sheets I and j come together there. Then if you solve this equation near there and impose this condition, you will find that it looks very much like a spectral network. So you will have three trajectories. It's an exercise to show that there is three and only three. And these trajectories, all of them have two things. They have orientation that's given by the real part of the differential on this trajectory. And so you can put an orientation, and this trajectory is a solution on that equation, so you can label by ij, and you label with a third index, which will be this little n. So it's this difference. So here is another technicality, which is everything you compute, everything you do, but for physical reasons, only these trajectories represent physical, like represent solitons or things like that. But the important thing is they always, all the physical, in this case it's 0 because, right? All the physical content is on this difference. So you are kind of adding some gauge freedom here. Because if I have a solution, you see, if I have a solution for this equation, I just can shift n plus 1 and I also plus 1, and I will have automatically another solution. So for each solution, there is always automatically an infinite tower of solution. You are supposed to quotient by that tower, and that's an artifact of working on the logarithmic cover, which is part of why some people think this approach is kind of nasty. But as I said, well, if you have a better one, come and tell it to me, to my face. Sorry? Lambda in this sense. Log f, yeah, yeah. No, you will get different trajectories. You will get different trajectories. The idea is after all that is fixed. Yeah, yeah, yeah. Very good, yes. So what's the question? Why these trajectories depend on the choice of lambda? Well, because this, okay, to say it in a short way, because these trajectories themselves are not the Lagrangians I'm looking for, if you want. Well, they will depend. This equation is on sigma tilde. They will depend on lambda. But these trajectories are not the special Lagrangians that are going to be. That should not depend on. Mm, well, okay, as I said, the thing is these trajectories are not the Lagrangians we are looking, but what will happen is that what you are going to look is that at the special thetas where these trajectories kind of degenerate, right? So they become like this, and they become some closed cycles in in uh, in sigma. That can be lifted to sigma tilde, but they also project to closed cycles in sigma. So those are the guys that are ultimately my Lagrangians on the Calabi-Yau threefold. These are supposed not to depend on lambda. No, not when I have a way to lift them to the Calabi-Yau threefold, to the conic bundle, and then they don't depend on lambda. Then they are special Lagrangians. Then I have to write the some holomorphic treeform on the full Calabi-Yau, and then this will be they will lift to some special Lagrangians on the full Calabi-Yau. No, the threefold doesn't depend on lambda. I just wrote the threefold before. That form doesn't depend on your choice of lambda because it's the form on the full on this x there. The x that is just this. It is like this. Right? So if you h is like then you have this this is like this tree form like du dv and you do this integral over a. No, exactly. Yeah, that's what. Yes. But these networks, yeah, it looks very dependent on lambda, and indeed it is. But the claim is that the numbers at the end won't depend on lambda. This one, no, I mean this depend on. I mean, at some thetas this will appear. Yeah. That's right. Yeah. This curve is this. No, yeah, it doesn't depend on lambda. Okay, this one does. Okay, sorry. This one, the degeneration doesn't depend on lambda. No, of course we believe. I mean, I cannot prove it. The network itself depends on lambda, but the Lagrangians so they depend only on d lambda. For different values of theta. Yes, indeed. That's a very special value of theta, yeah. If, say again? Yeah, sure. What is theta physically? That's hard to explain. But at this point, theta is the angle of the special Lagrangian. Like when you lift this Lagrangian to when you lift like this once to x, they are going to have you know that the holomorphic tree form restricted to the Lagrangian is going to be a phase times the volume form of the Lagrangian. And sorry. Is the depth of the central charge, yeah. Yeah. I mean, the central charge is just the period, in sigma tilde, the central charge is just the period with respect to this lambda. Okay, where was I? Okay, so let me, very good. Well, that's why we had Sivasic after, so let me tell you, okay, what these trajectories, what make these computations kind of different from the spectral networks. So the main difference is that the situation where these trajectories intersect, the trajectories intersect. So near a branch point, it looks pretty much the same, but the big difference is where these trajectories intersect. Because if you have something like this, let me write it for you, something like this, right? So if you have I different than k, then you can have a guy here, a newborn trajectory that will have these labels. So this again is kind of very similar to the spectral network, but with a new label. You just sum this one. This is M and this is N. Okay. However, the main difference is that you can have a situation where you can have like this. You can have I equal than K. So you can have like this. So you can have like this situation. Orientation is important. Then typically on a spectral network, you don't get anything here. They just go through. But here you get an infinite tower of trajectories. Actually, you get, if you want 4 infinite towers of trajectories, you get trajectories that are of this form. I will write them here. They will sum in this way. You will have some trajectories that are like this. And you will have trajectories that are usually forbidden in the spectral network world, which are trajectories where you can have II, right? So when you have those trajectories, this equation becomes really simple because these two cancel, but nevertheless, you still can have a non-trivial solution. So you have something like this. So this k, well, I use the same k for all of them, but this k is labeling each of these tower. I didn't wanted to write like K1, K2, K3. So, okay, yeah, just like this. So this is the shape it's going to have when these two type of trajectories intersect. So now, okay, very good. So now, yeah. How you mean emanate can be known? Oh, you don't know where this come from. They don't have to emanate from a branch point necessarily. Sorry? Yeah, then it's 0. Then this have to be 0 if it comes from a branch point. But it may come from something like this. These two? Oh, well, I didn't know where they come from. They can come from who knows. But well, you said they cannot have M or N non-zero. No, because you can have this. You can generate also these guys. Yeah. I should have. Yeah. Yeah, it is, I mean, yeah, there is, yeah, I should have wrote here, I forgot. There is, you had to set usually some logarithmic cut that lives on some of the sheets. So every time you cross it, depends how you cross it, this label can go up by 1 or go down by -1, right? So you can have this situation. Yeah, otherwise it will be very simple. Yeah. Okay, good that you have some of your collaborators on there. Okay, so now. That's right. That's right. What? Sorry, who? This or this? Which one? Yeah. Yeah. These two pictures shouldn't be surprising for you if you look at spectral network. Like you would say, oh, they look the same. That's what you're doing, this thing. But this one is different, right? That's right. That's right. But we don't know other way to solve this problem. Yeah, it's just I saw he mentioned this is because you have an infinite number of sheets. Okay. How we proceed? Okay, so then now that I introduced the network, and I have okay, you have about 15 minutes to introduce non-abelianization map. So what is non-abelianization map? So again, this is something that comes from spectral networks, and what you have is what you usually have on again, if you're familiar with spectral network, if not, is okay. You have some U1 flat bundle that I'm going to call abelian bundle. This is flat, so this is not U1, a GR1 line bundle on sigma tilde, and the network gives you a map. A map is an equivalence between a flat connection on a line bundle on sigma tilde to a flat connection of a vector bundle over the base. In this case is C, which is simply just C star. So this is non-abelian. So this connection, flat also. So typically the rank of E will be the number of sheets in the case of spectral network again. But in this case, you have infinite number of sheets. So you have like an infinite rank E. So how are you going to deal with that? So so for a point X in C given a spectral network that's not degenerate, that's non-degenerate, that was supposed to talk about that for the jumps, but in a spectral network that's not exponential network that's not degenerate, and you take X over this, then E at this point X is kind of an infinite sum, of line bundles, L, where P is all, I will write it like this to write not much, P minus 1 of X inside sigma tilde. So, sorry for being a bit, oh well, I mean, it's kind of okay. Right, so you have infinite tower of that, so infinite rank vector bundle, but that's okay. That doesn't stop us to actually compute things. So you still can compute things. So the idea is that you want to express the holonomies of this non-abelian connection of infinite rank along a path, some path that lives inside sigma, inside C. You want to express this holonomy in terms of holonomies of kind of in terms of, or let's say this is going to be in terms of, this is going to be a function of some variables that I call it to call xa, where xa are the holonomies along path a's of the abelian connection, okay, where a is path, some path here in sigma tilde. So that's very abstractly what you want to do. So you want to express this in terms of this. So that is the non-abelianization procedure. So how you do it? How you do it? Well, you just have to use the properties of having a flat connection, and that some holonomies are trivial. Yeah, exactly. So for every x, so xa satisfies some algebra. So xa and b is xav. If a v concatenate, remember that these are open paths. This can be open paths. All of these can be any. They can be open paths if you want. Open in general. If they concatenate and zero otherwise. So now what you do is you express this this holomorphic thing, this holonomy thing in terms of x. So how you do? This is okay. If you have, let's say, this is your network. This is your network, and you have a path here, like P, that doesn't intersect. Let's say P doesn't intersect the network. Then the holonomy along P of the non-abelian connection is going to be simply the sum over all the lifts of this path to all the infinite sheaves, right? Here, P, I, comma, and like this. So this is what we call, okay, first I have to do this trivial thing. So this is what we call the diagonal, because it's kind of diagonal. And then you have to say what happens if your path cross the network. So if your path cross the network, there is some version of the spectral network detour rule. So in that case, what you have, if you have now let's say this, and you have a path that crosses the network at some point z, so let's say this is P, then you divide P into P0 and P1, and your holonomy around P of zeta non-abelian of this flat connection is the diagonal of P0, right, this one, times E to some operator that depends on the type of this path. So this path, if it's ijn, is like this, and in principle depend on this point, but this you can change if you want, just labeled by the entire E wall. Okay, and this is the E of. So what is this? What is this? And that's the non-trivial thing to define. Oh, that's it. So this is defined as this. And I'm going to say what's this in a second. And also there is this mu a's, which are going to be, in general, they're going to be some integers, and xi. So what is this gamma? So this gamma ij is all the paths that, if you have C, and here you have the Z, so all the paths that go from the I and I, so it's all the paths that go from this sheet to a point that project in Z to this sheet to J, comma Nj, such that Ni minus Nj equals to N, to little n. And these numbers associated to each of these paths is containing some invariants that are called 3D, 5D solitons. So it's some counting, some invariants that you can define. But the interesting thing is that once you know this rule, you don't need to actually compute any of these invariants. You don't need to compute any of these mu a's, because you just given some very simple properties of these mu a's, you can simply compute, you can just bootstrap them somehow, right? So how you get these numbers? As I said, you don't need to compute them, but if you have situations like this, you can take two paths like this, P and P prime, and then use that the holonomy of the non-abelian connection along P is equal to the holonomy of the non-abelian connection along P prime. So, etc. At appropriate points on the network, then using these equations, you can actually eventually get all the mu a's you want. Now, of course, in 5 minutes, I have to explain you how you use this thing to compute the invariants. Okay, so how you compute the invariants? So now finally, how you compute this invariance omega gamma? How you do it? So you still, what you have to do is that you have to look at what we call jumps of the jumps. You need to look at jumps of this non-alienization map. So in a nutshell, what happened is that there is some, as I was saying before, there is some theta critical, where the network degenerates. The most simple degeneration you can have is like, right, if you have theta slightly below theta critical, you have, for example, these trajectories, and when you go to theta critical, these trajectories become like this, right? And after you move a little bit above theta critical, you get right this kind of thing. They pass through. So the idea is to understand what's the jump of the non-alienization map given in this case. So, for example, if you take a path like this, you take a path like this. So let's say here that cross exactly where the jump occurs. Then, in order to compare, in order to get this number, what you want to do is to compare the non-abelianization map before and after the jump. So what you will get then, and this is kind of, if you want, conjectural, or okay, is that f of p at theta minus, at theta plus, or theta plus is some transformation of f of p at theta minus. And this kappa acts on these xa's such that basically it only acts non-trivially on 2xa in this type of crossing. So in I comma n is like x p I comma n. This means the lift of this to that sheet times some function that I will call q of x, and kappa also of p j comma n is x p j comma n times q of x to the minus 1. And this assuming, let's say these are ij type. These are ij type. This is kind of a simple case. You can do more complicated cases where this function q of x is supposed to take the following form. It's supposed to take the following form, k1 infinity 1 plus xk gamma, and this is here alpha k gamma, where this gamma is precisely this cycle. This cycle is gamma. The cycle that you get after the network degenerate. So these numbers here, this alpha k gamma, are some integers. Oh, xk gamma is just is defined with this way. So xk gamma is xk gamma c is like holonomy along k gamma c of the abelian connection. Gamma c is like it's like a lift of this guy. So oh, I'm sorry. What is yeah. K copies. K copies of gamma c. Yeah, it's a closed path. So I can take gamma c is closed. This is closed. Yeah, that's correct. Because otherwise I have to put a k upstairs. Huh? What's I mean, we can write this. If that makes you happy. Yeah. I'm sorry. Yeah, that's. Where was I? Oh, this. So with these integers. So okay, this was incredibly fast, but so the invariant is encoded in these integers. You may think the invariant is exactly equal to these integers, but it's not. So I need one more formula, and this then I leave you guys free. I still have 5 minutes. Oh, 5 minutes for this formula. Then I can bother you for 5 more minutes. Okay. So the question is how you get this alpha k gamma. So I have to say maybe a lot of the reasons the papers we wrote are so long and so technical and so unreadable is because a lot of the effort goes into computing, literally comparing these two guys, these two f after a jump, and computing kind of by hand those alphas. So a lot of the work goes in computing those alphas. I wish I can give you an example. Yeah, only on examples, of course. I mean, come on, I'm a physicist, I do examples. No, in the examples, in the examples. I mean, even simple examples are very convoluted. That's the thing, because you have to deal with all this infinite and a lot of pain goes into it. But well, that's part of the spice of life. So so after you have this lambda, you can write some alpha. So notice that this alpha, I explicitly, though, in the alphas I put alpha k gamma, because they can be different for different case in principle. They can be different from different case. That's as I said, you just have to compute them in case by case. So you can form a cycle. So this is a closed cycle. So this is a closed cycle. You can assemble a cycle, a closed cycle. And again, sorry for being a bit vague on this, But then you have the basis afterwards to clarify many things. You assemble a closed cycle taking all the p's of this. These are the degenerate subnetwork. So in principle here I show, well, I erase it, but I show how one single path degenerate, but okay, there can be many other paths in the network degenerating, and you have to compute this alpha looking at many different paths inside C. So you can take a union of lift of all these paths with these numbers here. So remember that this x can be replaced just by the path, the wall of the network where this x belongs. So I just put that. And here pi minus 1, so the lift to sigma tilde. So this is really ultimately a path, is a closed cycle in sigma tilde actually, is infinite copies of it. That's again because we are working in this stupid kind of gauge non-invariant setting where we have the infinite. So when you lift it, you will have infinite copies of a closed cycle in sigma tilde. And at the end, the class of this cycle, or if you want the class of one of the, here I can put a little n to say one of the, you just take any copy, one of the representative of this cycle is going to be proportional to the class of this guy, because of these alphas. So this alpha is going to assemble together. So the proportionality factor is this guy. So this is the invariant you are looking for. It's if you want, this is the definition of this omega, our definition of this omega. Like you compute the alphas, you put this together, you look for it until it looks like that. Sorry. Say again. Yeah. So this is omega is the way. The omega is of course not going to be one. Correct, exactly. That's it. This omega is it. So you can take this k gamma, you lift it to the Calabi-Yau threefold, to the conic bundle. Then you look at the mirror if you want, and you compute the DT invariant of the mirror, and it should be exactly the same as this number here. That's a conjecture. Which example? So we checked essentially three. There is this, of course, there is this one. So mirror of this. So this means mirror. So I should write when. So that's the mirror curve. So just that. All of the omegas we compute were computed before. All the omegas we compute, as I said at the beginning, were computed before. Exactly. Yeah, that's what I meant. Yeah. Exactly, on the B side. On the complex. Well, okay, here it's unfair to call this side A or B because I'm working with objects with stability, so I have mix of parameters from A and B model. That's right. There are some conjectures and some, I know in the math literature, of course, there's some old conjectures also by Thomas and Yao and Joyce, but I don't know to what extent these things were computed explicitly. Maybe you know. Hmm? No, not this way, at least. I mean, so maybe one have to clarify. There are some examples, like let's say, okay, this is one, but we also can do this other curve that you will recognize as the mirror of P1 cross P1. So this, in physics, this has this so-called geometric engineering limit, which means there is a limit where the exponential network on this can be compared with the spectral network on the same curve with a meromorphic differential. And then some of the invariants can be computed in the spectral network setting, but some. If you want to really compute the mirror, all the mirror of the dt, there I have to clarify these are all rank 0 dt, like they don't have d6. Then you have to do it this way with the exponential story. So we did essentially, we had these two examples, and Sivasic is probably going to talk with something related to this example, maybe. So we have this example, and we have the, essentially we didn't write them all, but everything of genus 0 with punctures we can technically do. I mean, those are not so hard. Of course, the hardest becomes this one that are genus 1 or higher, because you start, that means in the mirror you have this non-trivial, non-compact D4 brains. So we have, no, I mean, basically this family of genus 0, and this one is the ones we have in our papers. We compare numbers, yeah. Quiver description. Yeah. See, I think Sivasi is going to talk a little bit about that. Yeah, I didn't talk anything about how to compare with the quivers. Yeah, no, I didn't. I actually didn't talk anything about mirrors. But by the way, I finished. It kind of this the question session kind of. Yeah, please. Yes. Very good. Uh, that will I will like to maybe discuss that more in detail, because we tried. You can do something like that, but in practice we didn't find any benefit of working. It is. Which formula? This formula. Yeah, it is a wall crossing formula. I mean, that's part of the heuristic that we well, I didn't say the word wall crossing, sorry, but yeah, I mean, this is, but okay, but yeah. It's okay. It's kind of the detour rule for when this extra cycle gamma appears. But I have to say that this formula also was, of course, was appeared before on these spectral networks. But yeah, I mean, it's like there is an extra detour when I erase it. That's the problem. But right, we had like this P, and we had this kind of thing that came together, right? So this, yeah. Hmm. Yeah. I mean, that's what you are describing. Maybe Pietro. It, but it must have interpretation in terms of I- there must be an interpretation in terms of the Bakwa of this 3D theory. Yeah, okay. That's the physical interpretation. But to get to the 3D theory, it will take me a little bit. So I can say some words after if you want. What do you mean? How do you incorporate the vector? The spirals. But which spiral? Like that from branch point to the. When you do this, okay, here I wrote just some lines, but when you do this, of course, there can be other strands that don't become, that they may not become together at this theta critical, but still, if I'm computing this holonomy, I have to take on account all the strands, which will include. Oh, I don't know if I understood this question. Yeah, I mean, depends. There are some situations where these ones are going to appear. Usually, no, I mean, okay. There is a case, for example, this one. This one has that situation. I mean, in this case, if you go to theta critical, you have like one branch point, one function, and you have some state like this, but then you have infinite. There is an infinite amount of degenerate walls in maybe, okay, maybe yeah, we can see it later. Yeah, that's right. The most simple. No. This case, these are not open DT or not open, just closed DT. So for C3, it's kind of very, the ones we compute is super simple. It's just K D0 is just omega corresponding to K, which is just all of them are -1. Yeah. Yeah. Yeah, that formula. If there are no more questions, let's thank Mauricio once again for a very... Thank you.